Welcome to the 2023 GCSE Physics Higher Paper 1 that we're going to run through today. Now, question 1 starts off looking at the national grid and it's looking at the role of a transformer. You need to complete the sentences. So transformer X causes the potential difference to do what? Now, transformer X is what we call a step-up transformer, so that means it's stepping up the potential difference. So that means we get an increase in the potential difference, and at the same time that causes the current to decrease. Those words have to be in the right order. Two nice straightforward marks to start us off with. Now, although it says in this next question, 1.2, use the physics equations sheet. As far as we're aware, you're not going to have the equations sheet for 2025, so you can ignore that bit. So you just need to know these equations, and there's only one option. Power is current squared multiplied by R. Now, this is a typical exam question. You just have to pick out the correct formula, and then the next question is always using that formula. So we're going to be using power as current squared multiplied by resistance. We now need to substitute in our numbers. We're given the power is 1.6 times 10 to the power of 9. That equals I squared, so that's going to be 2000 squared times R. We've got our first mark just for substituting in the numbers correctly. The second mark comes from making the resistance R the subject of the formula. So we need to divide both sides by 2000 squared. So you end up with 1.6 times 10 to the power of 9 divided by 2000 squared. When you plug all those numbers into your calculator, it comes up with a nice easy answer of, or round number of, 400 ohms. If you're going to go wrong at any point, it's forgetting to square the current. So don't forget that bit. Then on 1.4, again, we need to know your formulas. In this case, there's no symbols that you can use to make this one shorter. So efficiency equals, in this case, it's useful energy output. Useful E output divided by the total energy input. You just need to know your formulas. It's as simple as that. And then, of course, the next question, it's worth 3 marks. If you don't know the previous answer, it's very difficult to get any of those marks. So we've got efficiency is useful energy output divided by total energy input. We're being told that the total energy input of the national grid is 34.2 gigajoules. We were given the efficiency. We've now got to work out the useful energy output. So we're just going to substitute our numbers in. Now, the good thing with this question is we're given the total energy in gigajoules. The answer needs to be in gigajoules as well. So we don't have to worry about any conversions in this case. So substitute our numbers in. Efficiency is 0.992 equals, so it's going to be the output, or useful output, divided by 34.2. Now, to get output by itself, all we need to do is multiply both sides by 34.2. So it means 0.992 multiplied by 34.2. Put that into your calculator and you end up with 33.9 gigajoules. Now that question is total out of 10. Hopefully you got 10 out of 10 on that one. Now in question 2, we are looking at the specific heat capacity of iron. So the iron block the student used has 2 holes, one for the heater, one for the thermometer. And you can see that in the diagram clearly. So before the power supply was switched on, the thermometer was used to measure the temperature of the iron block. The student left the thermometer in the iron block for a few minutes before recording the initial temperature. Explain why. Well, it takes a few moments for the thermometer to adjust to the actual temperature of the iron block, so it's to ensure that the thermometer was at the same temperature as the iron block. So the thermometer at the same temperature as the iron block. So a bit of common sense there, and it's a nice easy mark to start off with. Now below we've got a graph that shows how the temperature changed after the power supply was switched on. The energy transferred to the iron block between 5 and 10 minutes was 26,000 joules. So we've got a value for energy, so that's energy, so I'll highlight that. We've got a mass of 2 kilograms. We've got to work out the specific heat capacity of the iron. Use the information from the graph and the physics equations sheet. So this is where you will need to use the equations sheet, because this is using our specific heat capacity formula. So if you remember, that is energy, E equals mc delta theta. So that is energy transferred is mass times the specific heat capacity multiplied by the change in temperature. Now we've got the energy provided, we've got the mass, we've got to calculate the specific heat capacity. Now the reason this is worth 4 marks is because we need to use the graph. We've got to work out what the temperature change actually is. Now we're looking at between 5 and 10 minutes. So we need to use our graph to work out exactly what the temperature change was. So I reckon that is 28 degrees, and then up here, draw a cross, be careful with this scale, it's 54 degrees. So before we can substitute our numbers into our formula, we need to work out the change in temperature. So delta theta equals 54 minus 28, which gives you 26 degrees. We're now in a situation where we can substitute our numbers into the formula. So we have energy 26,000 equals mass, which is 2, multiplied by C, which is our specific heat capacity of the iron, multiplied by 26. That means that C, specific heat capacity, is 26,000 divided by 2 times 26. That means, and the numbers are quite nice to you here, this simplifies down to 500 joules per kilogram degree centigrade. You don't have to remember the units on this, the units will always be given for you on that one. But that's 4 nice easy marks. And then 2.3, the student repeated the investigation but wrapped insulation around the iron block. What effect will adding the insulation have had on the investigation? Now there's a clue here, there are 2 boxes to tick. Now don't think that the exam board are trying to catch you out and think there are 3 correct answers. There aren't. Likewise, there's not one correct answer. You have to tick 2 boxes. Even if you don't know a second answer, just have a guess and you might actually pick up the mark. So which ones are correct? The calculated specific heat capacity will be more accurate. Well, if we're insulating the block, that does seem quite a sensible option, because it means that more of the heat is staying within the iron block. So yep, that seems more than reasonable. The iron block will transfer thermal energy to the surroundings at lower rates. Yep, again, that seems quite plausible, because that is the whole point of insulation, reducing unwanted energy transfers to the surroundings. The power output of the heater, well, that wouldn't be affected by insulation. The temperature of the iron block will increase more slowly than expected. Well, no, we're insulating the block, so if anything, it will heat up quicker. The uncertainty in the temperature measurement will be greater. And that's just not true either. How well our thermometer works isn't affected by whether our block's insulated or not, so that's just not true. Okay, that's the end of that question, and then moving on to question 3. Here we've got an electrical circuit used to heat the windscreen of a car. Each resistor in the circuit represents a heating element. So 3.1, the 12 volt battery supplies direct potential difference. What is meant by direct potential difference? So this is where the polarity of the potential difference doesn't change. Essentially, it means that the direction of the potential difference doesn't change. So if you talk about, the best answer is to say the polarity of the potential difference does not change. Or you could say the direction of the potential difference does not change. Either way, you're going to get your mark out of it. Alright, again, we're back to knowing our formulas. This is charge flow, energy, and potential difference. So E equals QV. Again, this just comes back to you need to know your formulas. Because if you look at the next question, again, we're going to be using that formula to calculate the charge flow. So really this 3.2 and 3.3 is a case of you're either probably going to get 4 marks on this, or you're going to get 0. Don't know your formula, you've got no chance on getting any of the marks on 3.3. So we start off with E equals QV, because that's the formula we're going to need to use. We've got to calculate the charge flow. We've got a 12 volt battery, so there's our potential difference, and it's transferring 5010 joules of energy. So there's our energy. Substitute the numbers in. So we've got 5010 equals Q, that's our charge flow, that's unknown. V is 12. So we've picked up our first mark on the calculation now by substituting in the numbers correctly. We now just need to get Q, make it subject to the formula, so we divide both sides by 12. So Q equals 5010 divided by 12. Put those numbers into your calculator and your answer comes out as 417.5 coulombs. If you did round that up to 418, you would still get the mark for it. So with this typical 3-mark calculation, you're going to have to do a little bit more manipulation with the calculation than normal. 1 mark for that line, 2nd mark for getting Q, making Q the subject, and of course the 3rd mark for getting the correct answer as well. Right, another maths question, 3.4, and here we're talking about how the ice forms on the windscreen at a temperature of 0 degrees centigrade. So we've got the electrical circuit transfers that number of joules of energy to the ice. We've got a mass of 0.015 kilograms, and we've got to calculate the specific latent heat of fusion of water. Now, again, in this case, we do need to use the physics equation sheet because this formula is actually on there. Now, hopefully you've realised the one we're looking for is energy transferred equals mass times specific latent heat of fusion. E equals ml. Now we just substitute in our numbers. So again, this calculation is worth 3 marks. There's going to be a little bit of manipulation needed. So we've got 5010 equals mass, which is 0.015, multiplied by L, which is our latent heat of fusion. That means that L equals 5010 divided by 0.015. That's going to give us quite a large number, and in fact we get 334,000 joules per kilogram, and that's worth 3 marks. Nice and straightforward on that one, assuming you can find the correct formula. And then 3.5, we're on to our 6-mark answer, and this should be one of the more straightforward 6 markers you're going to get. The electrical circuit was left switched on while the ice changed from a solid to a liquid and increased in temperature to 5 degrees centigrade. Explain the changes in the arrangement and movement of the particles as the ice melted and the temperature increased to 5 degrees centigrade. Now, that is quite a wordy way of saying what is happening as our material changes from a solid to a liquid. So this is just a state of matter question, and we're talking about some key terms you need to be talking about is that we're going from a solid, which is our ice, into liquid water. We've got the process of melting going on, and the important thing here, we need to talk about the changes in the arrangement and the movement of the particles. So in terms of the arrangement, you need to be talking about the solids being in that regular pattern, while in a liquid, our particles are more of a random arrangement. In terms of movement, the particles in a solid are vibrating around fixed positions. They're so packed in, they can barely move. That's why they've got those small vibrations. While the particles in a liquid are moving a lot more freely. The particles can slide past each other. So you're probably picking up at least 2-3 marks just for describing the arrangement and the movement, comparing the solid to the liquid states. Now, one of the things that's important to mention is that as our ice is melting from a solid, from solid ice into liquid water, the temperature stays constant, because as the ice changes state into water, the potential energy of the particles increases. So that's what our latent heat is all about. And then of course, as the water kind of gets warmer, starts increasing up to 5 degrees centigrade, the particles start to move faster, so it means that the kinetic energy of those particles also increases, so they're going to be moving more. And the other thing to remember is that this question is also looking at internal energy. Remember, internal energy is the total kinetic and potential energy of all the particles. So as our liquid water starts to increase in temperature, the internal energy of the particles is starting to increase. Now, if you include all that information in a very logical, clear account, you're looking at the full 6 marks. Remember, in this particular case, you only need to talk about the arrangement and movement. Having said that, I'd also link this to energy, because it's actually the energy of the particles which affects the movement and the arrangement. But that should be the kind of question where you're looking at gaining at least 6 marks every time. That whole question is out of 14 marks. Hopefully you got 14 out of 14 because there were some nice questions in that one. Okay, question 4. We've got a remote village in the UK uses a hydroelectric generator to provide electricity. So in one day, 2,500,000 kilograms of water passes through the hydroelectric generator. The change in gravitational potential energy of the water is 367.5 megajoules, and we're given gravitational field strength. So we need to calculate the mean change in vertical height of the water as it moves through the hydroelectric generator. Now it's saying here that we need to use the physics equation sheets. That's not the case for you guys, because you won't have the formula sheet when it comes to your exam. So this is one of those formulas that you need to know. The particular formula you need to be thinking about is gravitational energy equals mass times gravitational field strength multiplied by change in height. You've got some clues there, because we've got to calculate the mean change in the vertical height. We've got gravitational field strength, we've got the gravitational potential energy of the water being that, and we've also got the mass of water. Now this seems very generous for 4 marks, so you should be getting suspicious now, and you should be suspicious because of this. The megajoule. The megajoule is not our standard unit. We need to convert that into joules. So in this case, a megajoule, we need to multiply by 1 million. So 367.5 megajoules equals 367,500,000 joules. And that's the number we need to be using when we substitute our energy into the formula. Now, we've picked up 1 mark for doing that conversion. and put the numbers in. So we've got 367,500, and just be careful that you're writing down the correct number of zeros, particularly when you put this into your calculator. Don't want to lose any marks for making silly mistakes. We've got a mass of 2.5 million multiplied by our gravitational field strength of 9.8 newtons per kilogram, and the height is the unknown. We've now picked up a second mark for substituting our numbers incorrectly. The height, therefore, is going to be 367,500,000 divided by our 2 million multiplied by 9.8. Now, if you put those numbers in your calculator and you do it correctly, you should come out with a nice round number of 15 meters. So where do we get the 4 marks from? 1 mark for the correct conversion, 2nd mark for substituting numbers in, 3rd mark for making the height the subject of the formula, and then the 4th mark for getting the answer correct. Now, if you didn't convert your energy into joules, you'd only lose 1 mark. So your answer would be out by a factor of 1 million, but you could still get 3 marks because it would just be an error carried forward. Right, 4.2. The generator transfers 3 kilowatts of electrical power, and then we need to calculate the time taken for the generator to transfer 2.16 times 10 to 7 joules of energy. And it says use the physics equation sheet. So again, we can ignore that comment because we're going to be using formulas that you need to know. Now, we do need to take notes. We need to give our answer in standard form. Now, this calculation is worth 5 marks, so you should be very suspicious of this. Normally, I'd say if it's 5 marks, we're using 2 formulas, but in this particular case, that definitely isn't. It's definitely not the case this time. Now, we've got power, we've got time, and we've got energy. So, think about one of our power equations. Power equals energy over time. So that's actually the formula we're going to be using. Now, this seems a bit too simple for 5 marks. So we need to be suspicious. So there's going to be some conversion somewhere, and that's our 3 kilowatts. So 3.0 kilowatts. We need to turn that into standard units, which would be 3,000 watts. We can now use that number in our calculation. So substitute the numbers in that we've got. We've got 3,000 watts equals 2.16 times 10 to the 7 divided by time. We now need to make time the subject of that formula. So T equals 2.16 times 10 to the 7 divided by 3,000. Now put that number into your calculator and you end up with 7,200 seconds. Now at this point you might be thinking, great, that seems like a realistic number, and you're jumping up and down for joy that you've got all 5 marks. We haven't. Go back and check your answer. You've got to give your answer in standard form. So we now need to convert that 7,200 into 7.2 times 10 to the 3. And that's where we get the 5th mark from. So that question, very generous in terms of 5 marks. You get 1 mark for the conversion as our 1st mark, 2nd mark substituting numbers incorrectly, 3rd mark for making time the subject of the formula, 4th mark for the 7,200, and then the 5th mark for putting it into standard form. That's a great question if it comes up for you. Alright, question 4.3. Now, we've got a graph here showing the power output of the generator, how it varied during 1 year. And you can see that during the summer months, we get a big dip in how much electricity has been generated. Now, a solar power system is installed in a remote village in addition to the hydroelectric generator. Explain why this improves the reliability of the electricity supply to the village. Use the information off the graph. So you can see clearly in the graph that during the summer, the power output of the hydroelectric generator massively drops off. So theoretically, May through to August should be our warmer months. We're getting less energy being generated from hydroelectricity, but you would expect at that time of year that's the summer, longer hours of daylight, generally sunnier, so it means that the solar output would be much greater, and that means that there would be less variation in the total power output. So it just means for the second mark it makes things more reliable. So now on to question 5. So some isotopes emit nuclear radiation. So 5.1 is all about carbon-14 and how carbon-12 are both isotopes of carbon. Compare the structure of an atom of carbon-14 with the structure of an atom of carbon-12. Great question, 3 marks, really generous. So remember, carbon is carbon because they have the same number of protons. If they've got the same number of protons, they've also got the same number of electrons. This is where they differ in the number of neutrons. They have different numbers of neutrons. If you really wanted to, just to make sure you've absolutely guaranteed the marks, you could say that carbon-12 has 6 neutrons. You could say that carbon-14 has 8 neutrons. There's three nice marks to start us off on that question. 5.2. So carbon-14 is a radioactive isotope. Carbon-14 has a half-life of 5,700 years. So what does that half-life actually mean? So the 5,700 years is the time it takes for the number of nuclei, radioactive nuclei, in the sample to halve. So that's all we're looking for. Half-life, the time it takes for half the activity to go, or half the radioactive nuclei to break down. There's several different ways you can actually answer that question, but it's another nice simple mark. Right, so now we've got a table looking at some of the half-lives of some different radioactive isotopes. 5.3, we've got a sample of fluorine-17. It has an activity that is 1/4 of its original activity. Calculate the age of the sample of fluorine-17. Now, we're down to 1/4 of the original activity, so that means we've gone from, started off at 1, we'll go through one half-life, which would take us down to a half, we'd go down to a second half-life, which takes us down to the quarter. That means our fluorine-17 has gone through 2 half-lives. Look at the table, fluorine-17 has a half-life of 64.37. Multiply that by 2 to get the 2 half-lives, and that gives you the answer of 128.74 seconds. Now if you rounded that up to 129 seconds, again you would that would be absolutely fine. You would still get the second mark for that one. And then question 5.4. All the isotopes in table 1 emit beta radiation. Now we've got to explain which isotope would cause the biggest risk to a person's health based only on the half-life of each isotope. Now this one often catches people out. Now generally people will either go for nitrogen-18 or fluorine-18. They'll either go for one of the extremes. Now from past experience, a lot of people would have gone for fluorine-18 because the half-life is very long, and they've got this idea that there's lots of radioactivity being given out. However, because the half-life is very long, it means that the rate at which the radioactivity is given out is actually quite low. So it means that the correct answer is actually nitrogen-18, and it's because it's got the shortest half-life, which means it's got the greatest activity. So it means that because it's got the greatest activity, it'll be emitting the greatest dose of beta particles, which means that the person is likely to be absorbing that radiation. So it's nitrogen 18 due to it having the greatest activity or the shortest half-life. So it's rapidly giving off its radioactivity, which of course means that a much larger dose of radiation is being absorbed by the person. That's quite a tricky one, so if you did get all 3 marks on that, well done. Right, and then 5.5, people who work in the nuclear power industry need to be aware of irradiation and contamination. Describe the difference between irradiation and contamination. Now, these are definitions that you just need to remember. Irradiation, that is just exposure to radiation. Contamination is when you actually get the radioactive material actually on the person. So it actually ends up on the person. It is very much a common question now, looking at irradiation contamination. So just make sure you know those definitions. Now 5.5, again, this is a very common question. Give one health risk to a person working close to a source of nuclear radiation. Go for cancer or tumours, that will get you the marks. You can talk about DNA or genetic mutations, damages, kills cells. You could also talk about radiation poisoning or radiation sickness. Just saying you could die is not an acceptable answer. So it needs to be a very specific answer. Best bet, go for cancer or causes tumours. Right, and then 5.7. Workers in nuclear power stations are monitored to check the radiation they emit. A worker stands 1 centimetre away from a radiation detector. The amount of radiation the worker emits is recorded. Explain why the worker needs to stand close to the radiation detector. And it's because this is all down to alpha radiation. So some materials would emit alpha radiation, which of course, as we all know, which has a very short range in air. Remember, this is an explain question, so you need to give the reason behind it as well. Okay, and then 5.8, got a bit of maths to do again. So workers in the nuclear power industry are exposed to nuclear radiation. Now, pilots on aircraft are also exposed to to cosmic radiation from space. So we're given the daily dose caused by working in a nuclear power station. That's in millisieverts. And then we've got the hourly dose from cosmic rays to a pilot while flying. Calculate the number of days it takes for a nuclear power station worker to receive the same dose as a pilot flying for 24 hours. So the first thing to do is to work out what is the dose received by the pilot flying for 24 hours. So the pilot receives 0.0030 millisieverts per hour. How much in 24 hours? So we need to multiply that by 24. So 0.0030 multiplied by those 24 hours. So this is what happens to the pilot. Put those numbers into your calculator, and the daily dose of our pilot is 0.072 millisieverts. Now, a worker in a nuclear power station is receiving 0.00050. So how long does it take to get that dose? So we need to take that 0.072 and we need to divide it by the daily dose of a worker in a nuclear power station. And again, you just got to be careful, making sure you get the right number of zeros in this particular question. So if you do that calculation, that will give you 144. So the answer would be 144 days. So quite generous, 3 marks there, and it's probably quite a surprising answer really. That's arguably more dangerous to be a pilot than it is for somebody working in a nuclear power station. Right, that question, big question, worth 17 marks. Hopefully, you got the full 17 out of 17. Well done if you did. Okay, question 6. So we're on to the electricity topic now. We've got another 6 marker. So we've got a student investigating how the current in a filament lamp varies with a potential difference across that filament lamp. And we've got the graph of the results. So that should be a graph you're quite familiar with. Describe a method the student should use to obtain these results. You should include a circuit diagram. Right, so there's a massive clue here. Not only does it say include a circuit diagram, there's also a great big gap of blank space for you to draw it. Now, here we're measuring potential difference and we're also measuring current. So straight off you should be thinking we need a voltmeter, we're going to need an ammeter. We're measuring this for a filament lamp, so of course we're going to have a filament lamp in our circuit. We also need to think about how are we going to change the potential difference on this, or the current within this circuit. So we're going to need a variable resistor in our circuit. So start off with our power pack, something like that. Obviously you're going to use a ruler and make this a lot neater than what I'm doing here. So we need to put our ammeter in series, of course. We need to have our light bulb, or filament bulb I should say, and then of course we're going to have our variable resistor in the circuit. We're missing the voltmeter, that of course needs to go in parallel across the filament bulb. So quite a simple circuit diagram, and certainly to get to a level kind of 3 answer, which is 5 or 6 marks, you have to include a correct working circuit. Now, we're picking up marks without even actually writing anything just yet. You need to have the ammeter in series, you need the voltmeter in parallel across the bulb. Now, we need to talk about how we use the variable resistor would be used to help us vary the current and the potential difference in our circuit. Now, if you look at the graph, we've got readings at 1 volt, 2, 3, 4, 5 and 6 volts, and we've also got -1, -2, -3, -4, -5, -6. So we use a variable resistor to vary the current and the potential difference in our circuit. We take current readings at 1 to 6 volts every kind of 1 volt kind of increments. Obviously we record all this in a table. How do we get the negative readings? Of course we reverse the connections to the power supply. So reverse connections to get the negative values, and then we're into some of the kind of standard things that you should say in every method that you're writing. In fact, we need to take repeat readings so that we can calculate a mean. It means that we can discard any anomalies. Once we've got our results in the table, we've calculated that mean, we can then plot the graph, which is where the results are. And if you're including all those things, you're looking at 6 marks. So it's a relatively straightforward method, mainly because you've drawn the circuit diagram correctly. Now, like I said, to get the 5 to 6 marks, you have to be not just including the circuit diagram, but you also need to include how to get the negative values as well. And like I said, it's just reverse connections to get that. Now, the important thing is what people will have missed out is they'll not have looked at the graph properly and seen these particular crosses, which tells you what the different potential differences are that you're using. So make sure you use the information that's in front of you. Okay, so well done if you did get all 6 marks on that particular question. Now 6.2, we're now going to use that graph, which is why I've repeated it on this slide. It'll make it easier for you to see what we're talking about here. Now we need to determine the resistance of the filament lamp when the potential difference is 3 volts. Now again, it's saying use the physics equation sheet. That's a load of rubbish because you have to know these formulas, and this is probably the most important formula that you need to know. V equals IR. Remember, that's potential difference is current times resistance. Now you might be thinking, how do you do this? We've only been given the potential difference. You've got the graph to use as well, and there's a bit of a clue because it says use figure 6. This is our graph. So we've got a potential difference of 3 volts. We need to get the current from this. So again, be careful with these scales. It's much easier with a ruler. By my reckoning, when the potential difference is 3 volts, our current is 0.16 amperes. Let's substitute our numbers in. So at the minute, we haven't got a mark for the correct formula. We get the mark when we substitute numbers in. So you got 3 equals 0.16 amperes multiplied by resistance. We've now got a mark. Get resistance by itself, which is 3 divided by 0.16. And when you put those numbers into your calculator, you end up with an answer of 18.75 ohms. Now, if you rounded that up to 18.8 or even to 19 ohms, you've got your 3 marks. So well done if you did that. And then 6.3. Oh, this is a great question. It's worth 5 marks. So if you like your maths and your formulas, this should be straightforward. So we've got the current in the lamp is 0.21 amperes when the potential difference is 6 volts. We need to calculate the energy transferred by the filament lamp in 30 minutes. Use the physics equation sheet. Well, again, we've got to ignore that bit because you're going to have to know your physics formulas. But this is a great question. There's 2 ways in which you can do it. Now, the way I'd probably go down this one is looking at this bottom bit. We've got to calculate energy transferred, and we've got time. So that could be one of our power equations. So I'd be thinking we've got power equals energy over time. The only downside here is we don't have power, but if you look at the first sentence, we've got the potential difference, we've got the current. So we could use, to begin with, power is current multiplied by potential difference. That means the power is 0.21 multiplied by 6 volts. That comes out as 1.26 watts. We now use P equals E over T. We've got 1.26 equals E over, and again, they're trying to catch you out. 30 minutes we need to convert into seconds. So that is 30 times 60 gives you 1,800 seconds. Now, on this kind of question, even if you haven't got a clue how to do the question, if you've got a time in minutes, just convert it into seconds, and then there's a good chance you'll probably pick up a mark just for doing the conversion. So here you've got our numbers substituted in now. So it means that E equals, running out of space here, 1.26 multiplied by 1,800. That's going to give you an answer of 2,268 joules. Now that's one way to do it. There's an alternative. We could use, I'm just going to write on this other side, we could work out, we could do Q equals IT and work out what charge flow do we have. So if we did that, Q equals, we've got a current of 0.21. We've got our time, which we need to keep in seconds, so multiplied by 1,800. Now that would give us a charge flow of 378 coulombs. We could then use a second formula, which is energy equals charge flow multiplied by potential difference. I suppose if anything this is put a little bit easier because we're just multiplying our numbers through. So the energy equals Q, 378, multiplied by V, which in this case is 6 volts. Put those numbers in your calculator and you're going to get 2,268 joules. So in this particular case, there's two kind of perfectly reasonable methods to get the answer, and it's completely up to you which one you use. You don't get marked down for using one method rather than the other, but it's nice because you've got two options of how to work it out, and that's worth 5 marks. So that's a big chunk of marks. Well done if you did pick up all 5 on that. Right, then question 6.4. So the power output of a lamp is 1 watt when the potential difference across the lamp is 5 volts. A student predicts that the power output would be 4 watts if the potential difference was doubled. Explain why the student is not correct. Now, we've gone from 1 watt to 4 watts. Well, that means that the power is quadrupled. Now, theoretically, if we doubled the potential difference, we're only actually going to need to double the power. You'd also need the current to double. Now, if you look at the graph, that is not going to happen because we don't have a straight line. So that graph shows that our filament bulb is not an ohmic conductor. It means it doesn't obey Ohm's law, and it means that the potential difference is not directly proportional to current. Therefore, if we increase the potential difference, our current isn't going to double because the graph isn't directly proportional. So that is why the student is not correct. To get our power to quadruple, not only would you need the potential difference to double, you'd also need the current to double. Looking at that graph, that would not happen. Right, now that question is worth 16 marks. Well done if you got all 16. Right, number 7, we've got a baby bouncer, and its baby is in a harness attached to a spring that hangs from a door frame. So we've got the two different positions, position A, position B. 7.1, the baby bouncer should not be used with babies that have a mass greater than 12 kilograms. Suggest one reason why. To be fair, this is almost common sense. If the baby is above 12 kilograms, the spring may become permanently extended. You could also say that the extension of the spring is too great, so the baby's feet are always on the floor. They'd even accept that the harness or the spring may break. So lots of different possibilities, but like I said, it's relatively common sense for that question. So question 7.2 is a great question. So we've got our baby is in positions A and B. Well, at those points, the baby's stationary, so not moving. We need to describe the energy transfers as the baby moves from position A to position B. So at position A, the baby's stationary, suspended in the air. That means all the energy is stored in the gravitational potential energy. So that's the complete store. Now the baby's moving from position A to position B. So as we go from A to B, the gravitational potential energy is going to start reducing. That's going to get converted into our kinetic energy because the baby's starting to move. But don't forget, the spring is also going to start getting stretched. So we're increasing our store of kinetic energy and also the elastic potential energy stored in the spring. So by the time we get to position B, now position B, we're also stationary, so no longer moving. So all the energy is going to be stored in that spring. So it means that the only store we have at position B is in our elastic potential energy. And that's where we get the 3 marks from. So, nice question. 3 nice easy marks. Now the next one, 7.3, got a bit of maths to do. So we're being told that in one position the extension of the spring is 8 centimeters. The elastic potential energy stored by the spring is 4 joules. We've got to calculate the spring constant of the spring. Use a physics equation sheet. Now in this case we do actually need to use a physics equation sheet, and we need to use a formula. Elastic energy equals 0.5 multiplied by the spring constant multiplied by the extension squared. Now this is worth 4 marks, so this seems overly generous, so you should be suspicious. You should be suspicious, and rightly so. This 8 centimeters, we need to turn this into standard units, so we need to turn that into 0.08 of a metre. If people are going to go wrong in this question, they'll forget the conversion. Once we've done that, we can just put our numbers into the formula. And from that, we have 4 equals 0.5 multiplied by k multiplied by 0.08 squared. So we've picked up another mark just by doing that. So we're up to 2 marks, 1 for the conversion, 1 for the correct substitution. We then just need to get k by itself, so we end up with k equals 4 divided by 0.5 times 0.08 squared. When you put all those numbers carefully into your calculator, you end up with 1,250 newtons per metre. And there's your 4th mark. So, great question. The real catch here, and it's quite a common thing where they give you extension of springs in centimetres, you're always going to need to convert them into metres. Now that question's at 8 marks. Hopefully you got 8 out of 8. Well done if you did. Now question 8. So we're looking at models of the atom. So this could be as much of a chemistry question as it could be a physics question. Draw one line from each particle to the year it was discovered. Bit of a clue. Draw one line. Now, you just need, these are just stuff you need to remember. So the electron, that was J.J. Thomson in 1897. The neutron was the last of our particles really to be discovered. Neutron is 1932 by James Chadwick. The nucleus was discovered, that was Ernest Rutherford's work, that was 1911, and then a few years later Rutherford also discovered the proton, so that would be 1920. 2 nice marks to pick up. And then we've got some of the results of the alpha scattering experiments. So the nucleus was discovered using an alpha particle scattering experiment. You should all be thinking, yep, this is Rutherford's experiment, where he fired the alpha particles at the sheet of gold foil. And we've got a diagram showing the paths of 7 different alpha particles as they were fired at the gold foil. 8.2. Explain why alpha particle A takes the path shown in figure 8. Now, if you remember, an alpha particle is positively charged, and the nucleus is also positively charged. Like charges repel. That's not very clear. Like charges repel, and there's your answer. So the fact that the alpha particle got close to the gold nucleus, the charges repel, therefore it caused our alpha particle to be deflected back to where it came from, or back towards the source. Now in 8.3, explain why the path of alpha particle B is more tightly curved than the path of alpha particle A. Now this is just a case of that particle B passes closer to the nucleus. So what? So it means therefore it experiences a greater or stronger repulsive force. And that's why it gets deflected to a greater degree. So again, almost a bit of kind of common sense there if you remember that the alpha particle is positively charged, as is the nucleus. 8.4. What can be deduced about the atom from the path taken by alpha particles D, E, F and G in the previous figure? Tick one box. Now, those particles aren't deflected at all. That means they're just passing through empty space. That's the only answer we can go for there. And then question 8.5. How is the Bohr model of the atom different from the nuclear model of the atom? All Bohr did was he took Rutherford's work and he put the electrons into specific distances from the nucleus, which we call electron shells. So that is Bohr's work. He basically put the electrons in specific electron shells orbiting the nucleus. Now 8.6, this one is probably arguably the trickiest one I'd say in the whole paper, because this is almost touching on to paper 2 physics. So explain how an electron can move up and down between energy levels in an atom. This is also kind of linked to flame tests in your chemistry as well. So for an electron to move to a higher energy level, they absorb energy from electromagnetic radiation. So basically they get more energy, they become more excited, and they jump up to a higher energy level. And then they could also move to a lower energy level, because as the electron emits that energy in the form of electromagnetic radiation, it drops back down to a lower level. So linking that to a flame test in chemistry, as the electron drops down a level and gives off energy, it's energy in the form of that's where that's where the flame test colour actually comes from. Like I said, that's borderline almost a paper 2 question. Now that question is worth a total of 10 marks. Well done if you did get 10 out of 10 on that. Okay, so last question, and we haven't had a gas pressure question. You're always going to get this with paper 1 separates. So we've got somebody pumping air into a car tyre. We need to complete that sentence. So air particles in the tyre move quickly in. Remember, what do our particles in a gas do? They move quickly in random directions. So anything different, any direction would give you the mark there. Now 9.2, when the tyre is at the correct pressure, pumping more air into the tyre causes the pressure to increase further. The volume and temperature of the air in the tyre do not change. Explain why the pressure increases as more air is pumped into the tyre. So go for the obvious one, the first mark. We've got more air particles in the tyre. So what? That means there's a greater number of collisions with the tyre wall per second. And there's the 2 marks. So don't forget the obvious one, there's just literally more air particles, and because that means there's going to be more collisions per second, that's where the increased pressure comes from. And so the final question, 9.3. The air pressure in a car tyre changes if the temperature of the air in the tyre increases. Explain why. So as the temperature increases, it means that the air particles have increased their store of kinetic energy. So it means that they are moving more. Now if they're moving more, there's going to be more collisions with the walls of the tyre per second. Obviously every collision exerts a force. That means that there will be more force applied. So not only do we have more collisions, but also the speed of the collisions is going to be greater. So more force applied in our collisions, or in these collisions, and that means that greater force per unit area means equals greater pressure. Greater pressure in the type. So remember, this question is one of those annoying questions where it just says that the pressure changes. Make sure you're talking about that fact that the pressure does increase to make sure that you get at least 1 mark. So that's a nice question, 4 marks. It's one of those questions, comes up frequently, whether it's talking about the temperature going up, temperature going down. Make sure you know that one. Okay, so that's the final question. So that was worth 7 marks. Total paper is worth 100 marks. Hopefully you got 100 out of 100. Well done if you did.